All right, guys. So last class we started to talk about ideal gas, okay, and we emphasized that ideal gas is a very simplified model of the real gas, where we kind of ignore uh, the space occupied by the gas molecules themselves, which we viewed all the collisions between the gas molecule to be completely elastic, and essentially we simplified, okay, every aspect of the real world molecules, okay, and try to put gas in a like very abstract and ideal model. Like, okay, what do you do that for? Now, the reason of doing all that simplification is that once you simplify it, now the gas behavior can actually be described. Okay, some of the gas properties being described with a very simple and straight calculation model, and that calculation model is called the ideal gas law. Okay, and how simple is it? Well, one equation, okay, four changing variables, one constant. That's it. Okay, and these four variables, of course, are some of the most important properties of gas. P here is pressure. Okay, and the unit that we use in ideal gas law calculation for pressure, although there are so many different units for to describe pressure, okay, in different systems, but the unit that we use in ideal gas law is atmosphere, okay, ATM. V is the volume that gas occupies, okay, and in ideal gas law we use liter L to represent it, to count volume. Now N here is number of moles of gas. Okay, obviously the unit would be mole. Okay, T here is temperature. Okay, the unit we use in ideal gas law calculation is absolute temperature scale, Kelvin. Okay, and of course, why do you use Kelvin? Okay, now, if you use, why can't we use Celsius or Fahrenheit? Okay, well, the problem is both Celsius and Fahrenheit temperature scale involves 0 degree. Okay, you put that 0 into the ideal gas law, you pretty much instantly invalidate your ideal gas law, because you're saying that your pressure and your volume of the gas at that 0 degree Celsius or Fahrenheit, okay, the pressure and the volume, one of them need to be 0. And you know that's not the case. Okay, at 0 degree, well, 0 degree Celsius is pretty much the temperature outside right now. You know the gas pressure don't disappear. You know certainly gas still occupies volume. Now, and Kelvin temperature scale is a scale where you only have positive temperature, because the lowest, okay, is absolute 0. All the other temperatures are higher than that. Okay, and the conversion between Celsius temperature and Kelvin temperature is actually real simple. It's in this class we're going to use it as the Kelvin temperature equal to degree Celsius plus 273. Okay, there's a 0.15, beyond the decimal point. In this class, at this level, we're not bothering with that. Okay, whatever Celsius temperature you have, add 273, you get your Kelvin temperature. It's very, very important that in your calculations regarding gas, okay, in any of the calculations that we do today, if you use temperature, that temperature better be in Kelvin. So put a mark here on your notes that this is probably where half of the mistake comes in ideal gas calculations. Oh, I just forgot to turn it into Kelvin. Okay, and R here is the ideal gas constant. It has a set value, 0.08206, and it has the unit of liter times atmosphere over mole K. Well, you already know where these units are coming from. There's the atmosphere, there's the liter, there's the mole, there's the K. So, all right, now, for the atmospheric pressure, okay, now, 1 atmosphere, okay, equals to, there's so many different units for pressure, okay. 1 atmosphere equals 760 torr. Torr is one of the, I believe it's like belongs to the English system, but pressure unit. It could also equal to 1 torr actually equal to what we call 701 millimeter of mercury, okay, and that also equal to the metric system 1.01 times 10 to the fifths Pascal of pressure, okay, and you can eventually turn it into 14.7 pound per square foot if you want, okay, but I don't need you to remember these conversions. If in the final exam we test you on calculations of this with different pressure units, we'll certainly give you the conversions. Okay, you just have to make sure that you remember to turn it into atmosphere. Okay, now of course with the ideal gas law, then the simplest kind of ideal gas calculation would be, well, out of the 4 things, P, V, N, and T, R is always going to be provided. Okay, you don't need to memorize constants, I told you that, and just it's going to be provided to you. So with those 4 variables, if you know 3 of them, you better be able to calculate the other 2. Okay, so a simple example here. What is the volume of 1 mole of ideal gas at 0 degrees Celsius and 1.00 atmosphere? Okay, and also this temperature and this pressure, 0 degrees Celsius and 1.00 atmospheric pressure, okay, is actually such an important combo for physical conditions in chemistry situations that it actually have its own name. We call it the standard temperature and pressure, or in short, STP. So if you see these 3 letters together in capital letters, you know it represents, and if it's a gas problem, you know it's representing 0 degrees Celsius and 1 atmospheric pressure. Okay, so you're looking for volume, you already know moles and pressure and temperature. Okay, so rearrange your equation to show volume. V should equal to nRT over P, and N is 1 mole, and R is 0.08206 liter atmosphere, mole K, so mole cancel. Temperature, remember, it needs to be in Kelvin. So degrees Celsius, 0 plus 273, so 273 K. So Kelvin cancel. divided by pressure 1.00 atmosphere. Atmosphere cancels, so you got only liter left, which is the volume that we want, and the result here is 22.4. And if you had any kind of high school chemistry background, you probably remember this number, okay, 22.4. This is the volume of 1 mole of gas in a standard temperature and pressure, okay? 1 mole of, and think about this now. This is called the molar volume of ideal gas. In any other physical states, solid or liquid, you would not see a molar volume, because 1 mole of solids or liquids would occupy completely different amount of volumes. Only in gas. Now, regardless of how much, what kind of gas you're dealing with, if you view it as an ideal gas, now 1 mole of that gas at 0 degrees Celsius and one atmospheric pressure should occupy about 22.4 liters of volume. Okay, now, and of course, if real gases, you will have slight difference to the 22.4, but it's kind of usually in a give or take kind of range. Now, and now, all right, so this, of course, is the simplest kind of ideal gas law calculations. Knowing 3 things, looking for the other, okay? And all you need to do is rearrange the equation, plug and chuck, and make sure you know to convert the conditions into the conditions that's in your ideal gas constant. Volume for liter for volume, ATM for pressure, Kelvin for temperature, and then you're all set. Okay, so that's easy. Now, what other use do we have now for ideal gas law? Okay, now traditionally, after people discover ideal gas law, okay, it has been used as a source, okay, for people to calculate, to find out the molar mass of a given gas. And you look at this and you go, well, you just told us that pretty much all gases behave similarly, and they all occupy 1 mole of it, all occupy the same amount of volume. Like, what do you mean by now we can calculate different molar mass of different gas? Well, let's give you an example. Calculate molecular weight of a gas if 8.8 grams of it occupies 4.48 liters at 0 degrees Celsius and 1.00 atmosphere, or STP. Okay, so first of all, once you know it's a gas and you see it's a calculation problem, always write this out. PV equal to nRT. Okay. All right, so now what do we want? We want molecular weight. Okay. What do we know? We know volume, we know temperature, and we know pressure. Okay, now, so how do I get molecular weight? Well, pressure, volume, and temperature gave you number of moles. Okay, and once you get number of moles, if you know the mass of the gas, can you get molar weight? Molecular weight is grams per mole, right? You have grams, and you could calculate a mole. Is that really a problem? No, not at all. Okay, so rearrange the equation here. N equal to PV over RT. So 1 atmosphere, 4.48 liters, 0.08206 liter atmosphere. So both cancel. Mole K times temperature 0 degrees Celsius, 273 K. So this calculation tells you that you have 0.20 mole of gas. All right, once you get the mole, molecular weight should equal to 8.8 grams over 0.20 mole, and that's going to give you 44 grams per mole. So, pretty easy stuff, right? Now, okay. Another use of ideal gas law, you can also use it to calculate density of the gas. How? Well, let's see. What is the density of a gas at 20 degrees Celsius and 740 millimeter of mercury if the gas has molecular weight of 54.6 grams per mole. All right, so again, you see gas, you see calculation. Let's write PV equal to nRT out. Okay, now, and what do we know? I know T, I know P, shoot. I also have molar weight, molecular weight, or molar mass, okay? But I'm looking for density. There's no density in ideal gas law. Like, as much as I want to rearrange, I couldn't, because density is not there. And also, out of the 4 things in ideal gas law, I only have 2. I don't know volume. I don't know number of moles. So, how am I supposed to do that? Well, let's think about this. Now, first of all, just from the last problem, you know what molecular weight is. Molecular weight is grams per mole, right? Okay, how did we get grams per mole? We used the grams of stuff divide by number of moles. What is number of moles? Number of moles is N, right? So molecular weight essentially is grams over number of moles. Okay, let's plug that into this equation here. Because from here I can say N equal to grams over molecular weight. Right? Now, so what if I use this to replace the N in this equation? I ended up getting PV equal to grams over molecular weight times RT. But you still don't have the density. Well, hold on a second. What is density? What does density equal to? Density of gas now should be mass distribution over volume, right? Mass is grams. Oh, volume is something we know is V. Density equal to grams, mass over volume. I do have grams and volume in the equation I have now. Let me try to rearrange that. So if I move things around, okay, I would have pressure times molecular weight equals to gram over volume times RT. Okay, and that's density. Okay, and replace this with density. So let's use capital D to represent density. And then rearrange it. You ended up getting the equation density should equal to molecular weight times P over RT. Now, do we have all these? I have P, I have T, I have P, I have T, I have molecular weight, P, T, molecular weight, and I have R. So 54.6 grams per mole times pressure is 740 millimeter of mercury. Make sure you turn it into atmosphere. Each 760 millimeter of mercury is 1 atmosphere, so that cancels, over 0.08206 liter atmosphere, so atmosphere cancel, mole cancel, okay, times temperature, 20 degrees Celsius, 273 plus 20, okay, Kelvin cancel, and you ended up getting grams over liters, which is a density unit, and this calculation gave you about 1.8 grams per liter. Okay, so do you really need to memorize this equation? If you could, I mean, it makes your calculation a little easier with the condition provided, but even if you couldn't, as long as you know your PV equal to nRT, now, I believe everybody understands what molecular weight is. I believe everybody understands what density is. So this is kind of all plug and chug and algebraic rearrangement, and we ended up getting this equation. Okay, so these are some of the basic calculations that we could do with the ideal gas law. Okay, you could do a simple rearrangement to calculate one of the P, V, N, and T. You could use it to calculate the molecular weight of the gas if you are provided with the mass of the gas and some other conditions. You could also use it to calculate the density of the gas if you're provided with molecular weight of the gas. Okay, now, so all of those we focused on now. The calculation of one set of condition. Like, here is the gas, here are the conditions. Okay, now, there's also a different type of ideal gas calculations. Okay, and now, let's take a look at this next example here. A gas sample occupies 500 milliliter at 0.25 atm and 20 degrees Celsius. What volume would it occupy at STP? Okay, so you look at this question, this is a little different. Well, what do you mean by different? Well, we already said before, okay, STP means 0 degrees Celsius and 1 atmosphere, right? So let's look at the conditions provided. Now, there's a V, there's a P, and there's a T. Okay, and you can go, well, I can calculate N with that. Okay, but so if I have my PV equal to nRT, knowing P, V, and T, I should be able to calculate N. But am I calculating number of moles? No. I'm actually telling you to calculate another volume with another temperature and another pressure. I couldn't even label this as V anymore because I had a V. See the difference between this problem and all these previous calculations that we did that focused on PV equal to nRT? You would only have one V in those earlier questions. You would only have one P in those earlier questions. You would only have one T in those earlier questions. In this question, it seems like I have two sets of everything. Okay, so first of all, how do I label all of this? Well, I mean, if I'm having two sets of different things, let's label them V1, P1, and T1. And then I want V2, T2, and P2. So, shoot, how do I solve this? So this is the type of questions, calculations, we say that these have two sets of conditions. Okay, so once you see, let's say in the final exam, you see a gas calculation problem. Okay? Once you see it, I need you to be able to quickly determine, okay, if this is a two sets of condition problems or if this is one set of condition problem. One set of condition problem is the previous examples that we did. Okay? Yeah. Regular ideal gas law calculations, molecular weight calculations, density calculations. They all have one set of condition. But if you have two sets of conditions, we also have a standard operating procedure. Okay? So, what is that operating procedure? Yeah. You got to realize that the same sets of condition, okay, always satisfy the PV equal to nRT. So instead of writing one PV equal to nRT, now I want you to write two of them. First one is P1V1 equal to N1R T1. The second one is P2V2 equal to N2R T2. Okay? Now, what good does that do? Well, here's what good does it do. Now, both of your sets of conditions satisfy ideal gas law, okay, independently. So both of these two equations stands, and that means if I divide the two equations left side to left side, right side to right side, they should still equal. Okay? P1V1 over P2V2 equal to N1R T1 over N2R T2. Okay, so what good does this do? Well, first of all, you don't have to ever worry about R, because R is the constant, and they always get canceled. Now, and now, P1 I do have. Okay, V1 I do have. I don't have N1, but I do have T1. P2, I have that, 1 atmosphere. V2 is what I want, and I do have T2. And you go, well, you don't have N1 and N2, you can't solve this. Wait a second, what's N1 and N2? Read the question again. A gas sample occupies this much at this temperature and this pressure. What volume would it? Dang, they're the same gas sample. Oh, N1 absolutely equal to N2 because they're the same sign. What if N1 equal to N2? Duh, they got canceled. So what do you have? P1V1, P2V2 equal to T1, T2. Okay? Out of the 6 things here, you know 5. Can you get the last one? Of course you can. Rearrange your equation to show V2. So V2 should equal to P1, V1, T2, cross multiplication, over P1, P2, T1. And once you get this, just start to stick the things in there. 0.25 atmosphere, that's P1. V1, 500 milliliters, so 0.500 liter. And then T2, don't mess that up. 0 degrees Celsius, 273 K. P2, 1.00 atmosphere. And where's my T2? T1. T1 is 20 degrees Celsius, so 273 plus 20 Kelvin. Kelvin cancel, atmosphere cancel. You're going to have unit as liters, okay? Yeah. And anything else? No. Okay, punch numbers in my calculator. I get 0.120 liter. Okay, so this gas sample will occupy 0.120 liter, or you can say, to keep it consistent with the milliliter you had before, 120 milliliter. No, either way. No. So, oh, okay, since there's only 2 sig figs, so 0.12 probably be a better result. All right, so now you can see the difference, right? Now, and now, these type of two sets of condition problems, okay, don't always need to be, the, 6 conditions eventually. You can always do this, okay? And you always set out to cancel. Yeah. Okay? And actually, think about it. What if, okay, you have something like, okay, a gas sample occupies 2.0 liter, okay, at 6 atmosphere pressure. Okay. What volume it occupies at, let's say, 3 atmosphere. All right, let's say 4 atmosphere. Pressure. Let's make it 2 sig figs. I don't like 1 sig fig numbers. 6.0 and 4.0 pressure. So this actually looks a lot simpler, right? You don't really have that many number to deal with. But once you start to label them, this is a volume, right? This is a pressure. And then you ask what volume, that's the moment that you know that, okay, I have a 2 sets of condition problems, so V1, P1, and this is V2, which is what I want, and this is P2. Okay, so now that moment you go, well, I need my 2. P1, V1, N1 are T1. P2, V2, N2 are T2. Okay, so R cancel always, as always. What volume it occupies, same gas, same number of moles. Okay, I know P1 and V1. I don't know V2. I know P2. Oh, okay, so I gotta know T2 and T1. Nowhere in the question it mentions temperature. Okay, so let me give you a rule of thumb to ease your life when you deal with this type of questions. If a condition is not mentioned, assume it didn't change. Okay? Yeah. Because if you change and you don't tell me, then I can't do that calculation. Okay, so I can only assume that if you didn't talk about it, you didn't change it. Shoot. If all 3 of them are canceled, what do I got left? So P1 V1 over P2 V2, okay, equal to, well, if everything cancels, you got what? You got 1. Okay? Remember, don't turn this into 0, okay? That's not how canceling on top and bottom works. You cancel everything, you got 1, because that means everything's equal, top and bottom, okay? And that means P1 V1 equal to P2 V2. So V2 should equal to P1 V1 over P2, so 2.0 times 6.0 divided by 4.0, you get 3.0 liters. This is liters, this is atmosphere, and atmosphere cancels. Okay, so you got 3. Now, if a gas occupies two liters of volume at 6 liters of pressure, 6 atmosphere of pressure, then it will occupy 3 liters at 4.0 atmosphere pressure. Okay, yeah. And very similarly, okay, now you can go, what if in PV equal to nRT, okay? Now, V and N remain same. Then you would have V and N and R being canceled. So P1, V1, P2, V2, N1, RT1, N2, RT2. So V remains same, V1, V2 cancel. N remains the same, N1, N2 cancel. R always cancel. You ended up having P1, P2 equal to T1, T2. So if you're given 3 of those 4 conditions, you should be able to calculate the other one. Yeah. And by doing this, you actually can get a whole different bunch of equations to deal with different 2 sets condition problems. Okay? And that's how we deal with them. Okay? Once you identify its 2 sets, always come to this. Set it up, find out what's changing, what's not. Make sure you label all your conditions carefully. Make sure you don't plug them into the wrong position once you get your equation. You make sure of those 2 things, all these calculations are going to be plug and chug. Okay? Yeah. So, now, the next type of calculation we're going to introduce is called Graham's law. Okay. The Graham's law of diffusion. Okay. Now, what is that? Well, we all know. Okay. Now, gas flows. Okay. This is why you have wind on Earth. Okay. And when you release some gas at a certain point, okay, it's going to flow out, okay, occupy other spaces, okay. This is why you smell it when you have a gas leak somewhere in your house, okay. Now, that's how diffusion goes, okay. But how different gas have different speed of diffusion, okay. The Graham's law, okay, kind of predicting the speed of diffusion between different gases. Okay. Yeah. And it's a very simple equation. V1, the speed, diffusion speed, over V2, the diffusion rate between 2 different gases, okay, should equal to the square root of the reversed molecular weight rate between the two gases. Okay, now, and now, quick calculation example. How fast? What's the ratio between what's the diffusion rate ratio between neon gas and bromine gas? Okay, so very easily you can say speed of the neon over speed of the bromine should equal to the square root of molecular weight of bromine over molecular weight of neon. So put your molecular weight in. Neon, bromine is about 159.8 grams per mole, and neon is about 20.2 grams per mole. So cancel the unit, and you get about 2.81. So the velocity of neon is about 2.81 times faster than the velocity, than the speed of bromine. Why? Because neon is lighter than bromine. Lighter molecules diffuse faster. Essentially, that's the idea here of Graham's law. Okay, and now the last type of calculation of ideal gas that we're going to introduce here is this is called the Gay-Lussac's law of combining volumes. Okay, now, and what is this? I don't need you to remember the name. Okay, now this is actually something that you are kind of very familiar with. Well, what do you mean by that? Well, here's a example of what we're talking about now. If 6.0 liters of Br2 was reacted during the following reaction, how many liters of BrCl3 will be made? And equation is Br2 plus 3Cl2 producing 2BrCl3. Now, tell me what this question reminds you of. Okay, you see an equation, balanced chemical equation. Okay, yeah. You see the amount, this time in volume, of one of the components is provided. You're asked about the amount of another component of the equation. Yeah. Does that remind you of something? Raise your hand if you think of this. Remember stoichiometry? Isn't stoichiometry the same kind of thing? Now, here's why we're having this type of question. Okay, this rule or this gas law we're talking about here basically states that volume of gas involved in a chemical reaction, okay, has the same ratio or let me try to better state this. Volume ratio of gas involved in the chemical reaction equals to molar ratio. Okay, what does that mean? Okay, since we calculated before ideal gas, okay, number of moles of gas, 1 mole of gas occupies a certain amount of volume at a particular condition, right? So if those conditions are fixed, in a chemical reaction, likely you won't have a pressure and temperature change, okay? And then your volume ratio is your molar ratio. Now, so that makes this type of calculation just like your stoichiometry calculation. What do we do with our stoichiometry calculation? Moles of A times molar ratio gave you the moles of B, right? Now, the molar ratio is also the volume ratio. So 6.0 liters of Br2, and the molar ratio says each 1 liter of Br2 reacts with 3 liters of, or produce 2 liters of Cl3. Okay, so the result, of course, is 12 liters of BrCl3 made. Okay, and if you're wondering, is this really that simple? Yep. This is how easy it is. Now, we talked about quite a few different gas calculations in this part, okay? But every kind, as you can eventually see, turns into some kind of plug and chug, okay? And gas calculations are easy, okay? And I'll try to gather some practice questions, and you already see some on the recitation sheet that I posted the other day. But these are all the possible gas calculations you could see.